Hello, everyone, and welcome to the webinar. Today, we're going to be talking about cyber security for safety and equipment protection in mining. I'm Andrew Ginter, VP Industrial Security at Waterfall Security Solutions. Let's look first at who's coming after us. I've got 2 slides on the threat, and then I'm going to start moving into the solution. 3 slides rather. The first is this one. What's happened recently within the last 2 years? There's been a number of high-profile cyber attacks in the industry. Copper Mountain in Canada. I live in Canada. This is north of where I live. Copper Mountain went down for something like 6 days because of ransomware, if I recall correctly. And Arubis Copper Recycling, headquartered in Europe with facilities in lots of different places. Several of their facilities went down again, apparently because of a ransomware attack, down for a number of days. Khuzestan Steel in Iran was a high-profile case. Hacktivists got into the control system and started a fire. Nobody was injured. But there was apparently equipment damage and, again, a loss of production until the issue could be resolved. So that's sort of high-profile incidents. It's evidence that cybersecurity is a real problem in this industry. It's not something we can ignore. Volt Typhoon is something that is it's not metals and mining, but it's something to keep an eye on. Volt Typhoon is, a report came out of American intelligence agencies and other authorities that Volt Typhoon was Chinese intelligence agencies breaking into industrial facilities in power utilities, water utilities, other sort of critical infrastructures in the United States. And what they did was distressing. And, why are we talking about nation states? It's because most of us know that mines, the large mines, pretty much all are nation state targets. So let's look at nation states for a moment. I'll come back to the targeting. Volt Typhoon was allegedly, again, according to the best intelligence of the American authorities, was Chinese intelligence agencies breaking into the IT networks of critical infrastructures. What did they do in the IT networks? They did nothing. They sat there. How did they get in? The usual suspects: phishing attacks, stealing credentials, exploiting vulnerabilities in internet-facing services before they'd been patched. The usual ways to get in. What was disturbing about it was twofold. One is they were using what are called living off the land attack techniques, which means the bad guys were there was no in a sense there was no evidence that they were in the site. Usually, when the bad guys have taken remote control of one of our assets, there's a piece of malware on the site. It's called remote access Trojan, a rat. There's a piece of malware, and antivirus can find it. The good guys can find evidence that the machine has been compromised. With living off the land, the bad guys, the attackers, are using the tools that are normally on the machine to remote control the machine. They look like normal users. They act like normal users. They log in once or twice a week. They do a few benign looking things and they log out again. Intrusion detection systems have a very hard time finding these people. Why? Because there's no evidence that the machine has been compromised. So the authorities went in there and did a deep dive looking for evidence. They found evidence that the attackers had from time to time set a toe, dipped their fingers into the OT network. They'd reached into the OT network. They'd done some things in OT, nothing serious, and then just pulled back. Did not leave any permanent evidence of their attack in the OT network. And so the authorities are looking at this and saying, what does this mean? Why is Chinese intelligence doing this? There's no ransom demand. There's no sabotage. They're just sitting there. And they said, in their best estimate, they believe this is happening because the Chinese authorities want to maintain the ability to reach into OT and do something in the future. So this is distressing because, again, coming back to metals and mining, we all know that we are nation state targets. Mines, the largest mines produce, commodities that everybody needs. Lithium mining is a source of, geopolitical conflict. It's if a mine is strategic, producing materials that the nation needs, producing materials that the military needs, competing with geopolitical rivals who are, control a large chunk of a market, the nation states are going to go after each other in these mining IT systems and mining facilities. This is a risk. So this is why Volt Typhoon is so important here. Yes, it was a different industry, but this is the kind of thing that nation states can do to us if we're not careful. How does this work? Oh, I take it back. I'm getting ahead of myself. Let's look at the numbers. So that's sort of what's happening with mining. Let's look at the numbers first. Then how does it work? We're seeing, for the decade 2010. So these are all numbers out of the 2024 threat report that Waterfall puts out. The threat report's arguably the most cautious in the industry. We don't count near misses. We don't count, equipment failures. We count the numbers. We count deliberate attacks with consequences, with physical consequences, not stole information, stole some money. Deliberate attacks with physical consequences in heavy industry, and mining is in scope for this report, in the public record, no private disclosures. With those criteria, we have data in the appendix, the complete data sets in the appendix, if you're interested, indexed by industry, goes all the way back to 2010. For the decade 2010 through 2019, these attacks were mostly theoretical. Okay, the number of attacks that met that criteria bounced around between 0 in the year and 5. And then it changed at the turn of the decade. In 2019, there were 6 attacks. The next year, 2020, there was 18 attacks. The next year, there were 23. The year after, there were 57. The year after that, last year, there were 68 attacks affecting over 500 sites. Most of these attacks impacted multiple sites. Most of the attacks were ransomware, not all of them. Hacktivists are increasing, even faster than average. The fraction of hacktivist attacks is increasing faster than the total rate of increase of all the attacks. Why is that important? It's because ransomware wants money. If they shut us down, it's almost accidental. They are shutting us down. This is unacceptable. We need to fix this. But they're after money. Hacktivists are after damage. They're after shutting us down. The fire that was started in the Iranian steel mill, that was hacktivists. Hacktivists deliberately want to cause physical damage if they can. And with AI, they are getting more and more capable. And of course, in the largest mines, nation states are a factor because the largest mines are geopolitically strategic. So that's sort of the world we live in. We've changed from a theoretical state, why are we talking about this, to a state where these attacks are roughly doubling every year. How many doublings will it take before we're all in serious trouble? This is a train coming down the tracks at us. How do these attacks work? Really quickly, I'm not going to go through the whole slide. This is the modern attack paradigm. It's called targeted attacks. Some people call it advanced persistent threat. I don't like that word because nobody ever believes they'll be the target of an advanced attack, yet everybody is always rudely surprised when they are the target of an advanced attack. So I use the word targeted. The bad guys steal passwords. They, as I said, they trick people into clicking on attachments. They hit an internet-facing vulnerability before it's been patched, and they get into the IT network. And they take control of their first machine in the IT network, and then they pivot. That's the key word. They operate the compromised machine remotely. They use the compromised machine to attack other machines. And now they have 4 and 5 machines taken over in the IT network. They use those machines to look around. They find more valuable targets like the OT network through the IT/OT firewall. They reach through the firewall, they pivot through the firewall and take over assets in the OT network, pivot further until they can find the assets they're looking for, till they find something valuable, and then, work their will upon it. You might say, but isn't that what firewalls are for? Aren't firewalls supposed to stop that? Well, think about it. The bad guys, there's always a firewall between the internet and the IT network, isn't there? And yet, thousands of times a year, ransomware breaks into IT networks from the internet through that firewall. So clearly, the bad guys know how to get through these firewalls. What's concerning is that as we get deeper into mining systems, mining is extremely safety critical. There is so much that can go wrong there. And the problem is that a lot of the modern automation, not so much the older stuff, the modern stuff is computers, safety instrumented systems, security integrity level 4 systems that are software. And the problem is that these attackers know how to find vulnerabilities. They know how to reconfigure. They know how to log in remotely. They know how to manipulate software extremely well. And so now we have an increasing threat to the software systems that are protecting human life, that are protecting our equipment from damage. So this is the world we live in. This is why we're talking about cybersecurity. This is why so many mining owners and operators are talking about it. What are we going to do about it? Let's start with this. There's something new in the world called cyber-informed engineering. Bluntly, it's an initiative out of Idaho National Labs. Bluntly, it's a bunch of PhDs writing this stuff. It's really good stuff. I recommend it. There's 2 sort of major artifacts. One is a roadmap that basically says, look, someone needs to build a body of knowledge. We need to bring academics on side, et cetera, et cetera. It's a roadmap. It's not a recipe. And the second, they call it an implementation guide, but it's more of a framework. But still, it's, that's sort of the official CIE. What is it unofficially? Unofficially, it's a coin with 2 sides. One side of the coin is cybersecurity. Teach engineering teams, mining engineering teams, others about cyber threats. Again, the first 3 sides teach our engineers about who's coming after them and how they're coming after us. Teach engineering teams about cybersecurity mitigations. There's nothing new there. Okay, we've been singing this song in other industries for 20 years. Teach engineers about cyber threats and cyber mitigations. The other side of the coin, in a sense, is new. The other side of the coin is engineering. Think about it. If you work in one of these mines and you need to go down 1.5 kilometers underground in an elevator at the beginning of your shift, how would you like to be protected from a cyber attack that takes over the computer operating the elevator and sends you to your death? How would you like to be protected from that? Would you prefer an electromechanical governor where it's a centrifugal thing? If the elevator is moving too fast, the wheel spins too fast and trips and everything screeches to a halt and they rescue you? Or would you like a longer password on the computer controlling the engine? Most of us would like the electromechanical governor, thank you. this is the standard way to protect elevators. It's electromechanical. It's unhackable. In fact, what we'd like is 3 or 4 of these in parallel, so that if one of them wears out and fails to protect us, the other ones will. The people truly in the know say, Andrew, you're deceiving us. That's a deceptive question. You're trying to trick us. And they're right. I am trying to trick us. They say, if I was in that elevator and, I'm worried about the risk of a cyber attack, I want the electromechanical governor. I want 3 or 4 of them, because these things do wear out. And I want a longer password on the computer controlling the engine. And I want an absolute boatload of cybersecurity beside it, because this is my life on the line. That's the right answer. When you spend the coin, cyber-informed engineering is positioned as a coin. When you spend a coin, we don't choose one side or the other. It's a false choice that I offered you. We spend the whole coin. We spend cybersecurity and engineering both. But here's the thing. Where in the ISO 27001 standard, the cybersecurity standard, where is the centrifugal governor? No hint of it. Where is an overpressure relief valve in the industrial 62443 standard? Not a word of it. These are cybersecurity standards. When we talk overpressure relief valves, when we talk centrifugal governors, when we talk electromechanical protections, these are engineering tools designed to address physical risk, but they're powerful tools for addressing all risk. They should be applied routinely, systematically, universally to address cyber risk as well as physical risk. The risk of I don't know, the engine malfunctioning and the elevator going into free fall. That's the kind of risk that engineers have dealt with for a century. Engineers deal with risk to the worker, risk to the public, national security risk. Here's a new threat that is increasing sharply that the engineering profession needs to take into account with engineering grade protections. What is engineering grade? Well, engineering grade is deterministic. It has mathematically modelable failure modes, unlike cybersecurity, that's all software. It might have a vulnerability, it might not. When engineers design a bridge, we expect that bridge to carry a specified load for a specified number of decades in a specified operating environment with a large margin for error. I talked to a man who designs pedestrian bridges. He says, yeah, you calculate the maximum load of pedestrians that will ever be on the bridge, and then you multiply that by 8. And that's what you build the bridge to carry, because failure of the bridge under load, full of pedestrians, is unacceptable. Mining elevators are the same way. In most mining elevators, you have a cable holding onto this massive elevator that'll hold 20 or 50 people at once. And that cable is rated for the weight of the elevator and the maximum load of people in the elevator times 2. Okay, the cable is twice as strong as needed to carry that elevator. And the average elevator has 6 of these cables holding it up. The cables can carry 12 times the weight of the elevator. Why? Because failure of the elevator under load is unacceptable. So this is the expectation we have for the engineering profession when we're talking about cyber threats to safety. We expect our automation systems to stand up to a specified threat load for a specified number of years or sometimes decades, at least until the next opportunity to upgrade our security systems. And as we know in mines, upgrading these systems takes a long time. They happen at long intervals. We expect our automation systems to carry a specified threat load until at least the next opportunity to upgrade, with a large margin for error when worker safety or equipment safety or public safety is at risk. How do we do that? Well, we got to, we're talking about risk. when we're looking at mining operations, way too many of us are missing things. We might look at our safety, spreadsheet, the PHA, process hazard analysis, and look at all of the safety outcomes we need to prevent. Look at our mitigations and say, yeah, we're good, not realizing that safety instrumented systems are software. If the only thing standing between a cyber attack and disaster is software, there's a risk that the attackers are going to breach the software. We cannot count on software alone when we have truly unacceptable consequences. Another blind spot a lot of people have is they don't realize that our largest engines in our industrial facilities, in mines especially, the largest engines, are really very big. And if we have electric power at these sites, and sometimes we do, sometimes we don't, sometimes we're grid connected, sometimes we're not. If we are connected to the grid and someone disconnects the engine, a cyber attack disconnects the engine and reconnects it again a fraction of a second later, the engine winds up out of phase with the grid. And when that happens, the grid wins and the engine is forced back into phase extremely quickly, huge amounts of force, generally enough force to destroy the engine. This is something we need to take account of in our protection schemes. Protective relays are the software that's supposed to prevent that. Pretty much all protective relays nowadays are software. Again, if the bad guys can compromise software in all of our security systems, in all of our automation systems, there is a real risk they can compromise the relays. Something that almost nobody's been talking about, but we really need to start talking about, is brick devices. There's been a handful of attacks that brick devices. What is that? In the Ukraine attack in 2015 was the first time I remember it happening. The Russians broke into 30 substations, remoted into those 30 substations and told a TCP to serial converter device, just a little box that converts TCP to RS-232. Here's your new firmware, and downloaded all zeros. Now the device could not reboot. That's okay, we'll put the other firmware back on. Well, to do that, you have to reboot the device, and it can't reboot. You can't put new firmware back on it. You have to throw the device out and replace it, which was comparatively easy for that kind of converter. They're sort of commodity devices. How many of our PLCs could we replace on short notice if all of them were bricked? Or if all of the PLCs of one type were bricked? Usually we have spares. If we have 20 PLCs in a mine, we'll have, 10 spares, because over the lifetime of the mine, these things are going to fail. And by the time they fail, we probably can't buy them anymore. And, we're not ready to upgrade. So, sorry, I see questions coming in. Good job. If you have questions, ask them. So, we might have 10 spares. We might have used up half of them already because we're halfway through the expected lifetime of the installation. What if all of the rest of the 20 were bricked? Well, we only have 5 spares left. Where are we going to get the rest of them? In fact, if cloud systems are especially problematic. A lot of the modern systems, when we upgrade a mine, a lot of us connect stuff to the cloud. What if the cloud gets compromised, comes back and put new firmware in all of our brand new industrial internet devices? Doesn't just do it to us, does it to every mine served by that vendor. Now we've got thousands of devices out of action worldwide in dozens of mines. The vendor doesn't have thousands of spares. We're going to be without that infrastructure until the manufacturer can build the spares that we need. So brick devices is a risk we need to take into account, and way too many people aren't thinking about it. Remote access, I'm going to talk about in a moment. mines aren't built in the middle of town where people can live easily. A lot of us rely on remote access because it's just so hard physically to get out to the site. But here's the thing that worries, that should worry us, is, look, if I can remote into the OT systems, if I can reprogram the safety systems, that's a machine on the internet reprogramming the safety systems. How many machines on the internet should be able to reprogram our safety systems? The question is not how many do. The question is not how many are allowed. The question is how many are physically able if they steal enough software and keys. The answer is not very pretty. None of them should be able to, in my mind, yet we need remote access. So I'll come back to remote access in a moment. What we need to do is become more paranoid. Yes, the ransomware currently wants money. They don't currently mean to use their abilities to wipe us out. They could. I mean, what I forgot to mention earlier is that a great deal of ransomware groups nowadays are wealthy enough that they can afford to buy nation-state style attack tools from nation-state intelligence agencies. There's a market, a black market for these attack tools. Nation states and ransomware increasingly are using the same tools. They buy and sell them from each other. And so nation states are coming after us. Nation state capable ransomware is coming after us. Hacktivists backed by AI is coming after us. What we need to start doing is thinking about what happens if every CPU in the mine does exactly the wrong thing at exactly the wrong time. That's the worst case that we need to address in our safety thinking. How do we do that? We talked about cyber-informed engineering. If you have electromechanical safeties, electromechanical mitigations, the bad guys can't hack them. That's good. Not everything can have electromechanical safeties. I mean, what happens? What happens if a cyber attack, overruns the elevator too fast, and the electromechanical safety kicks in and stops the elevator? What happens? We shut the mine down until we figure out what's going on here. What else is at risk? Get these people out of the mine. We have an incident. We're stopped for as long as it takes to do the investigation, to persuade ourselves that our automation has been cleaned out, is safe to operate again. Often we want to replace the automation, not just clean it out, because we just don't trust it anymore. What if there's an attack residue left there? Now we shut the mine down. That's not what we want either. We can't afford to have the mine shut down for days or weeks or months for one of these investigations. So, it's not enough to say we have safeties, nobody will die. We also need to keep the mine running. So this is where sort of the concept of network engineering comes in. This is something new in the world. It's actually a collection of old techniques. A lot of this stuff is old. I mean, safety engineering's been around forever. Network engineering techniques have been around forever. This is my most recent book. It's cross-industry, but it has some mining examples in there. I'm going to give you one in a moment. And one of the the book's focus, it flies high and slow. Okay, the target audience is managers. You should be able to, if you're having trouble getting funding for a cybersecurity initiative at your mine, request a few free copies here. You see the URL on the bottom of the screen. You'll get that URL in your email as well. Send a few copies of this to your board of directors, or if you like, invite me to address them. This is what I'm good for. This is what I do. I try to explain the problem and potential solutions to business decision makers. That's the target of the book. One of the things in the book that I'm going to focus on for this presentation is something called network engineering. It's a collection of techniques, none of which is terribly new, but these techniques are focused on criticality boundaries. What's that? It's the boundary between a network with acceptable consequences and a network with unacceptable consequences of cyber compromise. An example, the business network: if you steal information, you suffer business losses. The OT network, if you compromise it in the worst way, people die. These are very different kinds of consequences. At that boundary between safety critical and business critical, that's where we need more than just a firewall. And I give some examples, I think on the next slide. Here we go. Here's a handful of examples. For our safety systems, we want our mine operators to be able to see the status of the safety systems. I mean, if one of the safety systems fails or malfunctions and we get an alarm on it, we need to know that so we can fix the wretched thing as quick as we can, because these things have to work. But how can we signal what's happening in the safety system out to the main mining control system without introducing the possibility of an attack pivoting, without introducing a pivoting path back into the safety system? We can do that with analog signaling. Run a 4 to 20 milliamp loop. Cost about $500 per signal. You can signal a 1 or a 0. You can signal an analog value, anything between 4 and 20 milliamps. Let's scale that to say 0 to 100%. So you can send a handful of values out saying, yes, I'm here. Yes, I'm alive. It's all good. Or, I just tripped the mine, because of cause number 3. Go look it up. That kind of signaling is not message-based. It's not TCP. It's not internet protocol. It's one way, and it's analog. You just can't send. You can't pivot malware or buffer overflows or other sort of the toolkit of nation states and ransomware and hacktivists. You can't pivot any of those toolkits through an analog signal. It doesn't work. So here's a way to monitor our safety systems without introducing a pivoting path. EPRI has a methodology as well for industrial internet. Similarly, they say if you want to use the industrial internet in your mine to monitor what's happening in the mine, in cloud systems, in AIs, in whatever, and have the business benefit from access to that data, do an engineering study of the internet, the industrial internet edge devices, the devices that are in the mine. Convince yourself that these devices are monitor only, that they physically cannot control anything in the mine. Not that there's a software switch that they can control or not. They physically are unable to control anything. And then deploy them to your heart's content. Send your data out to the world. Send it out to the world on the IT network. Send it out to the world on the internet, on the cellular network. Do not connect these devices to your control network, because we do not want the ability for an attack to pivot through the internet, through the cloud, back into these devices on our control network. Put them out on the internet. If they get compromised, we suffer business consequences. We lose a little money. We can deal with that. We can buy insurance for that. Nothing gets back into the mine because the devices are not on the control network, and they have no access to the control network, and they're not physically able to control anything. So that's the EPRI methodology. I've got some other examples in the book, but the most common example of network engineering technology is something called a unidirectional gateway. For the record, this is what Waterfall produces. But if we can introduce one layer of network engineering, what is network engineering? It is, formally defined as engineering grade prevention of the propagation of attacks through a network boundary. And in my example here, think of it, in layman's terms, it's engineering grade prevention of pivoting attacks getting through a network boundary. We don't replace every firewall in the mine with analog signaling. We don't replace every firewall on the IT network with a unidirectional gateway. We use network engineering at the criticality boundary to keep the bad guys out on the IT network, not into the mine. A few words on unidirectional gateways. If you've never been to one of the Waterfall webinars before, the gateway is a network appliance. Again, it sits at the criticality boundary between the mining systems and the business systems. The hardware is physically able to send information in only one direction. There's a fiber optic transmitter, a laser, on the sending side, on the mine side, there is a fiber optic receiver, a photocell in the circuit board on the IT side. So you can send from the laser to the receiver. You can't physically send anything back. There is no laser in the circuits on the IT side. It's not physically possible to send anything back. All cyber sabotage of operations is information. If we prevent any information getting back, we prevent all attacks getting back, or at least all online remote control attacks getting back. Just can't get through here. The software is, in a sense, the tricky bit. The software makes copies of servers. If we have an OPC server in the mine, if we have a Pi server in the mine, if we have a SQL server in the mine, the software logs into the server, once a minute, or sorry, not once a minute, once a second, whatever you configure, and says, please give me everything new. And gets a snapshot of 5, 10, 20 megabytes of data back, all of the latest stuff that happened in the last second since the last time we asked. We push that data out through the weird one-way hardware. Okay, no one else ever sees it. It's just the gateway software that sees it. And on the other side, the gateway inserts the data. It's another CPU. It makes a connection, inserts the data into an identical server. If it's OPC on the inside, it's OPC on the outside. If it's Pi on the inside, it's Pi on the outside. SQL to SQL, Oracle to Oracle. And now anybody on the business network, anybody on the internet who needs the data can get it from the business copy of the data source. Normally, send your queries, get your data, gets the same answers as the live system would have given, but nothing can penetrate to the mine through the gateway. Under the hood, you can run your finger down this divider down the center of the unit. You can verify visually that there is no cross connect. Nothing is cross connected inside the unit. It's really two separate units in one. Separate power supplies, hot swap power supplies on each side. The only connection is that fiber optic cable on the front. So auditors love this because they can understand it. If we're talking about making copies of stuff, though, you make a copy of an OPC server very differently than you make a copy of an Oracle server, because you're logging into this, OPC, you say, please give me all your values and tags. Oracle, you're saying, please give me for these tables all of the records with a timestamp greater than. They're completely different ways to make copies of stuff. And so we have these connectors. We have a ridiculous number of them, over 100. We can make copies of just about anything you have. In fact, when we come into a site, the question is not what can we make a copy of. The question is, what have you got, and which of these 5 or 6 or 8 things would you like to make copies of? And we deploy the correct connectors. The whole thing is simple. It's a network appliance. You put it in, you put it in sometimes in series with the firewall. Sometimes you replace the IT/OT firewall with this device. You put it in, you log into the web-based user interface, you activate the connectors you need, you configure them. It's 1 or 2 screens per connector. And then you're done. It just works. It's set and forget. I mean, it's distressing sometimes. I've been working for Waterfall for over 10 years, and I still go to trade shows, and people come by and say, unidirectional gateway, what is that? And I'm going, you've been using one for 6 years. We have? Yes, you have all of your plants. People forget that they have them because they're simple to set up, and then you don't have to babysit them, because even if there's a vulnerability in the software, if you forget to patch it or something, the hardware saves you. So you just don't need to focus on these things as aggressively as we need to focus on intrusion detection systems and firewalls and other sort of software mechanisms. I'm running short on time. I wanted to say just a word about remote access. The safe way to go from the internet into a mine, sort of an unbreachable way, is remote screen view. You call up your contact at the mine. It does take a person in the mine to enable remote screen view. We like an engineer, but you use who you've got. They have to verify that they're talking to you, that you're the real deal, not some AI deep fake. They're talking to you, And they turn on remote screen view, and you can start seeing pictures of, let's say, the engineering workstation. Now you can move your mouse out here all you like. You can't, you know, the gateway lets nothing back in. But you can be on the phone, give instructions to your person at the site, and say, please, bring up the system diagnostics. I see the error message there. I can, let's figure this out. You can see the mouse moving. You can say, no, that's not system diagnostics. That's communication. It's two further down. There you go. That's system. So you can work together. Everything's being filtered through the brain of the person on site. Okay. There is no way a nation state, a hacktivist can come in here and, unless they trick the person on site, put procedures in place. If you want remote access, have them call you, not you call them. So this is arguably the world's safest remote access system. It's entirely appropriate for mining systems when we need access to them from the internet. Another mechanism that's used sometimes when you need more routine remote access, or when you don't have somebody at the site, but you've got all of your software remote access security in place. You just don't want to leave that software system exposed to the internet for any length of time, because the longer it's exposed, the more likely it is the bad guys are going to get in there and take it over. I mean, the Chinese intelligence is accused of taking over hundreds of VPN servers all over the world. Because they exploited 0 days in these servers. So this is a technology, secure bypass. The gateway is one way out, nothing back. Secure bypass is copper in, copper out with a physical key. If you turn the key, the copper's connected. It's two-way, bidirectional, 1 gigabit per second for a limited period of time. So you call up the site, they call you back, verify that you are who you say you are. They turn the key and they give you 30 minutes. And you come in with VPNs and two-factor and all of jump hosts, all of the usual protections into the mining system. Do your thing, and after 30 minutes, that key pops back. The electromagnets separate. Nothing gets in again. So this is a way to give controlled, physical control over remote access to personnel at the mine. Again, I'm running a little short, but I've got a blog post on this. If you want to have a look at the Waterfall blog, it's a little hard to find. You got to go to OT Resource Center or something like this. And then, don't click on any of the industries, click on the thing at the left, or just Google Ginter, that's my name, mining abstraction. And you'll find the article. But basically, if we have to have cloud systems sending instructions into the mine, how do we do that? How can we do that safely? Here's one way. The scenario is, look, I've got not just a mine site, but I've got primary processing at the mine site. I've got materials processing. And what I pick up a load of ore, I drop it on the truck, 750 tons of it. The truck drives to the primary processing site. And while the truck is driving, there's sensors in the bed of the truck. There's sensors in the shovel. We're figuring out the nature of this load, so that the AI in the cloud, we're sending all that data out to the cloud. We're doing it so that the AI and cloud can optimally process that load and save us money, so that we don't have to use up our treatment acids or whatever we have. We save money by doing this optimally. But here's the thing: if let's say there's a dozen PLCs controlling the primary processing site, if the cloud AI sends in here's 1,000 timestamps and PLC names and register numbers and values, execute. If I look at that, I can't figure out if I'm going to damage equipment at the processing site. I'd be hard, and I've written a lot of code in my career, I'd be hard pressed to write code to reliably determine that this sequence of very cryptic instructions is safe. If instead we use abstraction and we say, okay, the instructions coming in from the cloud, we can send out whatever we want. What comes back in is, let's say, an XML file. And we say we've got a crusher that can only run at 3 safe speeds. Otherwise, there's vibration problems. So, it says crusher speed, low, medium, and high. LOW, MED, HIGH. If I have a furnace that can only go from 200 degrees to 800 degrees, anything above or below is ineffective, and anything above risks damaging the furnace, then I'll send in furnace temperature, and it's going to be a number between 0 and 100%. And you send in, basically you define a schema that is unable to express an unsafe configuration. You analyze the configuration possibilities and you say, these are safe configurations. Design a schema that can only express a safe configuration. Send that in. Now you're going to have to send it into a manufacturing execution system or a batch manager or something to interpret the schema and turn that schema into PLC names and register values. But that logic, the safety critical logic, is happening at the mine site, not out in the cloud where it's constantly exposed to attack. So that's the concept of safety. When we have abstraction, when we need to send information, safety critical information, back into the mine, send it in the most abstract manner possible. Send it in a format that makes expressing unsafe configurations impossible, as much as possible impossible. Dependencies is something else that a lot of people are talking about, and it's new. We haven't been talking about these more than about 2 years, and it's important. Think about that cloud service. The cloud service is out on the internet. If it goes down, can we operate the primary processing center anymore? Sometimes we can, sometimes we can't. Let's say we can't. So what we have is the safety critical mining operations that need network engineering, prevent anything from compromising them. And we have the business critical IT network. And we got that cloud service. That's a reliability critical component. If it goes down, the mine stops. So now we don't have 2 criticalities, safety and business. We have 3 criticalities. And we've got to apply some of network engineering tools to those 3 networks, not just 2 networks. We have several criticality boundaries. What do we do? One of the things we have to watch for is these dependencies, where we might have the world's best OT security system, and if IT goes down or if the cloud goes down, we have to go down. Well, what good did our security system do if a cyber attack took us down? That's what we're supposed to prevent with a security system. These dependencies are biting us over and over again. So what we need to do, one of the tools that people are talking about is rapid recovery. Because if we have something that's reliability critical, the question is, how long can it be out? If the cloud is down for half an hour and then comes back, we've lost half an hour's production on the day. We might decide that's an acceptable loss. And so the question becomes, if the cloud, or forget the cloud, let's say that's in the IT network. If that server is in the IT network and the IT network is wiped out by ransomware, the incident response team has to be trained to make a beeline for the reliability critical components that should ideally be on their own network, recover the entire network from virtual machines, from whatever, and bring it back up as immediately as possible. The mine picks up operation and off we go. But to do that, not only have we had to identify the dependencies that the mine has on these external services, we've also had to identify the dependencies. We have to apply network engineering to these external services. We have to identify their dependencies, because if they depend on Active Directory, which is still crippled, well, then it does no good to restore these. They don't work. So, dependency analysis is a new thing. Again, I talk about in chapter 5, and it's a tool for managing reliability risks. And for the record, I don't know if I've mentioned, the book is available for free. Waterfall sells technology, not books. If you ask for the book, we'll just send you a copy. So this is Waterfall. We've been around for 17 years, something like that. Um, I've been with Waterfall for this is my 14th year. We're, offices all over the world. We're deployed all over the world. We are trusted by mines. We're trusted by critical industrial infrastructures all over the world. We tend to be deployed at the largest and most consequential sites on the planet. That's what I had for you. Um, in summary, we're looking at roughly doubling every year. This is exponential growth in the threat environment. Something new in the world is the idea of applying engineering grade protections systematically, universally, to address cyber threat in addition to the normal physical threats they've been used for the last century. Network engineering is a collection of techniques. It's a way of looking at criticality boundaries. That criticality boundary is a new concept that really people have only been talking about for a handful of years. And it's a set of tools for managing criticality boundaries. Blind spots are bricked equipment damage. A lot of us, think about safety, but we forget about these risks, these threats to our equipment. And I've been talking a lot about engineering grade this and engineering protections that. Don't forget, cybersecurity, cyber informed engineering is a coin with two sides. One side is engineering, yes, and that I emphasize that because we've kind of neglected that side of the coin for a long time. The other side of the coin is cybersecurity. We also need cybersecurity. We need both. The question, when you spend that coin, you don't spend one side or the other. You spend both. The engineering side has been neglected. We need to take advantage of the tools we have on the engineering side, but we also need cybersecurity. That's what I had for you. Let's hit the question and answer. I was actually wondering, Natalia, are you on the line? Are you going to help me with the Q&A?
Yes, of
Hello,
course.
thank you for joining us. Very good.
Hello, Andrew. Thank you very much for a wonderful presentation, like always. We actually got quite a few questions from the audience today. Our first question is the mining industry considering what may happen with the advent of quantum computing and Shor's algorithm?
Short answer is I don't know. I am less familiar with. I'm bluntly, you've almost reached the limit of my knowledge on the mining industry here. I have been working hard in the last 18 months to come up to speed on how mining works. What are the concerns in mining? But I would not call myself an expert there. And the short answer is I don't know what the industry is thinking about that. What I will say is that I think about what's happening with quantum computing. It seems like now that, you have to wonder with quantum. People have been talking about quantum for a decade, and we still have RSA. We still haven't managed to factor prime numbers. So you got to wonder if quantum computer isn't going to go the way of fusion, where for the last 50 years, fusion has been 50 years into the future. I don't know, but when it comes, we're going to need new algorithms. To my knowledge, there have been algorithms proven mathematically resistant to quantum computing, and when quantum happens, if quantum happens, we're going to need to swap out our crypto. And so, as we're buying products, as we're buying technology, all technology that we buy nowadays has CPUs in it. Almost all that communications is encrypted. As we're buying that technology, we need to specify in our purchasing technology where we can swap out the crypto, or if you want, start using quantum resistant crypto already. It exists, is my understanding. So yeah, it's something to think about, but I don't know how high a priority it is for the mining industry specifically. Sorry.
I see. Well, thank you. Our next question is, How can we know if the information sent from the sender is received by the receiver?
Two answers to that, maybe three answers. That's a good question. We get it fairly frequently. The sender cannot know. The sender is blind. The sender sends it through the one-way hardware and gets nothing back. The sender has no idea if it's been received. The receiver knows what's going on. The receiver sees sequence numbers and error detecting codes, error correcting codes, sees heartbeats. There's a lot of information the receiver has, and the receiver is generally out on the IT network. And so if something goes missing, we missed a sequence number, the receiver can say right away, we've got a problem. Can send messages to my cell phone, can send email, can send stuff to the network operations center, can send syslog to the security operations center, you name it. All the alarm bells go off. The third answer is that generally doesn't happen. People imagine that, well, it's one way out. If I run a fiber optic cable under the ocean, there's going to be some losses. And this is why there's retransmission requests and stuff like this. Here's the thing. In a unidirectional gateway, the fiber optic cable is exactly this long most of the time. There's rare exceptions. And so you don't lose bits. And we have not just detecting codes, we have correcting codes. It's a proprietary algorithm, but it's more efficient than Hamming codes. But if you Google Hamming codes, that's the idea. There's enough redundancy in the transmission that if you miss some of the bits, or some of the bits are corrupted, you can recover the original message. You can correct, you can fix those errors. In practice, the only time people get these devices into their test beds, they put them through their paces, they find that in practice the only time that you actually do lose data is during scheduled downtime to apply security updates. You got to reboot the device on the receiving network. You have a gap in your data. When you do that, this is scheduled downtime, so you can have scheduled with somebody at the mine site. 5 minutes is all you need, saying, okay, you give them a phone call saying, I'm done my upgrade. Can you go and press the button for me? And they go to the user interface of the unidirectional gateway, web-based, local to the mine, press the button and walk away. What's the button do? It resends the last 6 hours of data by default. You can configure it. It's called a backfill operation, or some of the connectors, some of the user interfaces call it a backfill. Some of them, some of the connectors, they call it an archive. But either way, you resend the last 6 hours, or, it's configurable if you need more than that. And the receiver in the gateway says, what is all this? I've seen this. Oh, just wait, I haven't seen that. And fills in the gaps. And now you're back up to speed at the end of your scheduled, maintenance window for applying the security update. So the sender is blind, has no idea if it got through. The receiver knows. We know because the receiver tells us. And in the very rare cases where you do lose something, almost always scheduled downtime, you just press the button and resend it. It's called a backfill.
Okay. Our next question is on remote access solution, how you resolve if the vendor needs to upgrade the firmware of PLC?
The way I would recommend is you need a way to get that firmware to the mine site. You can email it, but you're going to need cryptographic checksums. You're going to need some strong assurance that the version you burned to a write once CD at the mine site from your IT network is the real thing. And once you've convinced yourself of that, it's a write once CD, it's stable, it can't be written to anymore. Again, use remote screen view. Have the vendor give somebody at the mine site instruction on how to apply that update. That, to me, that's the safest way to do it. You can use secure bypass, but I would prefer, for safety critical systems, I would prefer to see remote screen view used. It's stronger. It's the strongest kind of remote access. And again, when there's so much at mine sites that are safety critical, that's what I would recommend.
Thank you, Andrew. Well, we reached the top of the hour. Let's take one more last question and wrap it up.
Sure thing.
So our last question is kind of more broad. How likely is an attack on mining safety systems in the next few years?
I have no idea. The likelihood to me is the wrong question. Likelihood is a good measure for looking back for, when you've got high frequency, low impact events. You can talk likelihood, you can talk frequency. That concept makes sense. Looking forward, the likelihood of that attack depends upon the capabilities of our adversaries, their intent, and the opportunities, in our defensive systems. Well, the adversaries are nation states. They're essentially, they can develop whatever attack tools they need to get into us. The adversaries are ransomware, who are buying and selling nation state attack tools. They have the capability. The motive, well, maybe the nation states want to come after us, maybe they don't. Ransomware comes after everybody with money. If they do damage to us, it's kind of accidental currently. Will ransomware motives change a year from now? They're changing already. They are holding more data to ransom than encrypted systems in the past. So capabilities change fairly slowly. Motive can change very quickly. Intent can change very quickly. Hacktivists especially, their intent can literally change in the space of a heartbeat. They're watching a news report. They become angry at somebody, and they come after us because in that second they develop the intent to attack us. So it's unwise to base public safety and national security when we've got critical mine sites. It's unwise to base national security and public safety on our predictions of the bad guy's intent. And so it's prudent. What the engineering profession has been doing for a long time is basing their defenses on our adversaries' capabilities. Now, this is mostly in the physical realm when we're talking about terrorists, rather than trying to predict the intent of the moment. So, how long is it going to be? I don't know. Should we wait until we have one of those incidents before we put protections in place? That's not what the engineering practice tells us. The capabilities are out there. The capabilities of coming after us and causing serious consequences are widely available. We need to defend against those capabilities, not try to predict our adversaries' intent in the future.
Thank you, Andrew. Well, we've got a great interaction today from the audience, and we still have quite a few questions. And I'd like to mention that we'll reach out to all of you individually and answer them via email. Andrew, you want to add anything else? Any last word?
No, just again, send me the questions, and I'll follow up. And if I don't have the answers, I'll get the other waterfall experts who do have the answers. Thank you all for joining us. Thank you, Natalia, for helping me out here. I have a one-track focus when I'm on these webinars, and it's really hard for me to deal with the Q&A.
Yes. Always good to have help.
The threat report, send me email. You've got my email on the bottom there, firstname.last@waterfall-security.com. I'm happy to send you a copy of the threat report. We can get you a copy or 2 or 3 if you need them of the soft cover, the paperback book. Send me feedback. I hope you found the webinar useful. I hope you find the book useful. And if you don't, or if you do, let me know. I rely on feedback to try and produce, better materials in the future. So thank you for attending, and thank you for your future feedback, I hope. And thank you, Natalia.